but I can't see it. Yeah. Okay, now it is visible. Okay. So I'm making this recording all available to you, so that you can fall back upon in case you are missing something, and that I'm ensuring that this recording is done properly, so that students who are falling behind can at least get something later on to fall back upon. Okay, so now we are going to start the next topic, which is called data link control. Now let us try to understand what is this data link control. Okay, so far what you have understood is that we have two computers, right? And you have a sender, you have a receiver, and the sender basically sends these data, these bits, either in the form of digital signals using encoding schemes like NRZ, Manchester, differential Manchester, etc., or through analog signals with the help of modulation schemes like FSK, ASK, PSK, etc. Right? And if there is any error, the error has to be detected. But there is one problem that we have not gone through so far. Can you tell me what is that problem? There is one problem, right? So we have encoded the data in the form of signals and we have sent. We have attempted to detect whether there is some error that creeps in. But there is one problem that is very important when we are considering this scenario from the sender to the transmitter, whether whether the transmission happens correctly or not. Who can tell me what are the important issues that are still left out? Actually, the answer I have already told last week. Okay, so who can tell what is the issue? Anyone who can guess? Students, anyone? No one. Okay, let me tell it to you. The answer is basically controlling the flow. So I told you last week also that the sender is sending the streams of bits, the receiver is receiving, but you also need to ensure that the receiver should not get overwhelmed with the data, in which case the receiver will have no other way but to drop the bits, because there is a certain buffer capacity beyond which the receiver can do nothing but to drop the bits because it cannot store them, right? So the receiver cannot get overwhelmed by the sender. The receiver cannot get overwhelmed by the sender. It is also required not only to ensure that the flow of bits between the sender and the receiver is controlled, but also in the process, if there is some kind of an error that gets introduced, how to deal with it. So this is where this data link control, which is part of the data link layer, which again I will cover in another class. This layering concept I will cover in another class. So this data link layer basically deals with it. How to handle this kind of flow, or have a control over the flow and have a control over the error. So error control and flow control are what we are going to study. But before error control and flow control, we will study another thing, which is called framing. So framing means like these bits. I told you that we are going to take in blocks, etc. It is exactly the same thing, basically, how you are going to produce some blocks called frames out of these bits that are going to be received or sent. So these frames, you do not want, see, the problem is that you need to have certain fixed sized blocks to be sent and to be received. You cannot leave it like, infinite size kind of thing, which is like there is no fixed size. You cannot leave it like this. Why? Because if you do not have a fixed size, small sized block of bits, then you cannot really perform these checks that I mentioned earlier, and also what I'm going to cover now to ensure the control of the flow and the control of the errors. So for ensuring the smooth, reliable transmission of the data between the nodes, you need to take help of something called framing and flow control and error control. These are part of something called the data link layer, which we will cover in another class. So let us try to understand this framing concept. Let us try to understand this concept of framing. So in the data link layer, the task of the data link layer, which is also called the layer 2, is to basically separate the messages from one source to a destination, or from other messages to other destinations, by adding a sender address and a destination address. So this destination, basically this address, it defines where the packet is to go, and the sender address helps the recipient acknowledge the receipt. Now there is some mechanism for this addressing that we are talking about, which we are deferring for now, but we will cover when we talk about Ethernet later on. So the whole message, this is one thing, and the whole thing, and another thing is that if you are talking about a long message consisting of zeros and ones, as I told you, this whole message cannot be packed all together and sent, because if you do so, you are dealing with large number of bits altogether, so the frame is going to become very large. And if you have such a large frame, then this flow control and error control are going to be very inefficient. So that is the reason you need to basically have these fixed sized frames which are going to hold the data that comes from the other layers. So the data that comes, the actual data that comes from the other layers, plus the header and the trailer, plus some flag fields at the beginning, at the end, together basically forms the frame, right? Together forms the frame. So you have the actual data, the header and the trailer, and the flags at the beginning and the end, together forms a frame. So now you are talking about, at this level of abstraction, you are talking about the transmission of these frames. We are not talking about bits any longer. Conceptually, of course you have the transmission of signals and bits, etc., in the physical level, but conceptually, so here at this level, you are as if the sender data link layer and the receiver data link layer, as if they are transmitting frames between them. Okay, is this clear? Any question? Now let us proceed further. So unless you ask me a question, I wouldn't know, right? And I cannot see your faces also, whether you are sleeping, whether you are awake, whether you are playing games, whether you are on Facebook, what you are doing, it is hard to know, right? So students, you are in third year, take control of yourself. Okay. Okay. Now, um, so we need to produce these frames, right? Now let us try to understand two associated concepts. One is called byte stuffing. Another one is called bit stuffing. So let us start with the byte stuffing first. So in byte stuffing, you take a frame, okay, and you add a special type of byte, okay, when there is a character with the same pattern as the flag. Now the question is, what is this flag, right? So the question that you might ask is, what is this flag? So this flag at the beginning and at the end of a frame are basically 8-bit or 1 byte entities, which basically helps to demarcate the beginning and the end of the frame. In other words, at the beginning and the end of the frame, you have these 8-bit flags, which basically shows or which indicates the beginning of the frame and the end of the frame. So the flag basically, which basically is protocol dependent, signals the start or the end of the frame. Okay, it signals the start and the end of the frame. Now in byte stuffing, a special byte is added to the data section of the frame when there is a character with the same pattern as the flag. Why? The question is that why do we need to do it? Because if you don't, and in the actual data section, if you have this kind of bit pattern, if you have some bit pattern which matches the bit pattern that is used in the flag, then erroneously it will be identified to be the end of the frame, which is not correct, right? So that is the reason you have to byte stuff if that pattern basically appears somewhere in between. So in the data section, you need to do some stuffing with this extra byte. So this byte, if you are talking about this character data, then this byte is usually the escape character. This escape character has a predefined bit pattern. It is predefined, it is known, right? So it is this escape character which it is stuffed with. When the receiver basically encounters this escape character, it removes it from the data section and then treats the next character as the data, not a delimiting flag erroneously. So when the receiver encounters this escape character, it removes it from the data section and treats the next character immediate after that as the data and not the delimiting flag. So this escape character is introduced in order to save that particular group of bits to be misidentified as a flag. Is this clear? Any question? Now you can do this if you are talking about character data. Only if you are talking about character data. Okay. So for example, traditionally, when in the earlier days, the communication used to be only text communication. But nowadays, people are talking about audios, videos, and there are non-character, there are these things which are not just characters, right? So which are also transmitted. Okay, so That is where this byte stuffing basically can help to fix the problem of having the same bit sequence as the flag in the data section. So if you byte stuff, that erroneous misinterpretation, the erroneous interpretation of the of the actual data to be erroneously identified as a flag is going to be prevented. So what do? You do it with a escape character. Now this kind of thing actually you have done in your C programming also, right? Something very similar. You remember if you want to print some special character, right? If you want to print some special character, what do you do? What do you do? You proceed with a backslash. Do you remember? Right? So conceptually it is similar. Of course, the mechanism is different. So this is byte stuffing. Now there is something called bit stuffing also. So far we assumed that we are dealing with a stream of characters, right, as the data. So if you have the data section to be a collection of bits which will be interpreted by the upper layers as text, graphic, video, audio, etc., then you need to fall back on something called this bit oriented framing. Okay, so let us try to understand how this works. So let us look at this frame. So you have this variable number of bits which come from the upper layers, preceded by a header, followed by a trailer, and then you have these flags like this. This is predefined bit sequence. Okay. So most protocols use a special 8-bit flag pattern, this one, as the delimiter to define the beginning and the end of the frame, like this. So how is bit stuffing done? So in bit stuffing, basically, you add an extra 0 whenever 5 consecutive ones follow a 0 in the data, so that the receiver does not mistake the pattern, this 0, this flag pattern basically, for a flag. Right. So let us say that you have this data that comes from the upper layer, right? And what does it have? It has this 0, 1, 1, etc. till 0. Okay, like this. So you see, this could be misidentified as a flag because the flag has this particular bit sequence. So that's why what is suggested in bit stuffing is that whenever there are 5 consecutive ones, so you replace the 1 with a 0. Okay, and then it will differentiate from the flag. Now you see, not replace, sorry, you introduce with a 0. Now what happens is these two become 2 extra bits. Okay, this is not replacement. Okay, this is introduce. So you introduce a extra bit. So 2 bits are introduced in this particular example as the extra bits. Okay, and these are sent forward. Now this receiver also knows that this particular rule. So this receiver, because it knows this rule, it automatically it is going to, whenever it receives this kind of pattern, it is going to remove this 0, and it is going to accept the regular stream of bits to be the actual data. So that's about framing. And in the frame, how do you introduce some special mechanisms in order to ensure that the sender and the receiver, they can talk to each other in proper way. So now let us, so we know by now how to take this sequence of bits, streams of bits, and produce frames. We know how to produce frames. Okay, let us now try to understand that how we are going to control the flow and the error, which I talked about at the outset. So again, always keep in mind that we are talking about a sender, we are talking about a receiver, right? So in that backdrop, these sender and the receiver being connected over a link, let us try to understand this concept that I am going to talk about now. So flow control, formally, let me introduce to you. I explained to you what is flow control, but let me do it more formally. Flow control basically coordinates the amount of data that can be sent before receiving an acknowledgement, and is one of the most important tasks of the data link layer. In most protocols, flow control is a set of procedures that tells the sender how much data it can transmit before it must wait for an acknowledgement from the receiver. So very soon I'm going to show you different mechanisms of flow control. So I'm going to show you, how much the sender is going to wait before it can send the next frame. Okay, so there has to be some synchrony, some discipline that has to be established through different mechanisms between the sender and the receiver. It cannot be that the sender keeps on sending. The receiver, it doesn't care of the receiver whether it is able to process them, whether it is able to receive the the frames correctly or not, so properly or not, or whether it is getting overwhelmed, whether it is dropping the bits. It doesn't care. It cannot do like that. So there has to be proper synchrony between the receiver and the sender. The sender should know that when the receiver is ready and how much the receiver can basically accept. So this is where all these flow control mechanisms that I'm going to cover shortly is all about. Now, associated with flow control is something called error control, okay, which basically talks about what to do if there is an error that gets introduced, right? If there is an error that gets introduced, right? So what to do? So this is where you have these error control mechanisms. Now, this flow control and error control, these are quite strongly bonded. These are quite strongly bonded. In fact, these are so strongly bonded that some mechanisms are there where error control and flow control can be done at almost through the same kind of steps, right? These are like, these are very associated steps. So if you just modify the basic flow control mechanism slightly, you can get the error control mechanism. Just let us try to understand those. So these protocols that are there for flow control and error control, you can classify them to be of broadly two types. For the noisy channel, flow controls for flow and error control for noisy channel, and flow and error control for noiseless channel. For noisy channel, the mechanisms are stop and wait ARQ, go back N ARQ, selective repeat ARQ, and for noiseless channel, you have the simple mechanism and the stop and wait mechanism. So you will notice that we have stop and wait everywhere, right? So this stop and wait actually is a very simple mechanism, conceptually very simple. So which you can use for noiseless as well as noisy channel. For noisy channel, you need to have slight modification. So let us try to understand each of these, right? We'll start with the simple protocol, right? So simple protocol means what? So there is no flow control or error control. We have the sender, we have the receiver. We are talking about somewhere over here, this yellow part, right? So this yellow part basically receives the data from the higher layers at the sender. Again, these layers, etc., we'll cover in another class. So just for now, you assume that here actually we are receiving some data, and then we have to do something and send in the form of frames. So we are doing the framing and we are sending the frames to the physical layer. So these frames basically over the wire or over the medium get sent. At the receiver end, these are received, and then again the data link layer basically takes control of how to handle these frames, right? And then the actual data will be delivered to the receiver, right, in the higher layers, basically in the higher layers. Okay, so you see that the sender and the receiver basically will have to continuously keep on doing it forever. The sender does it forever, receiver does it forever. The sender basically, the data link layer in the sender device, it gets the request from the network layer, and the data link layer in the receiver end, it gets the notification from the physical layer. So essentially, this communication that you are going to have is peer-to-peer between the data link layer at the sender side and the data link layer in the receiver side. So that the data frames basically, as you can notice over here, the data frames basically travel in only one direction from the sender to the receiver. The receiver can handle the frame, any frame that it receives, okay, and then the data link layer of the receiver will immediately remove the header that was introduced at the sender side to the frame, the extra header that was given, and then it hands the data back to the network layer for further processing. So what is this network layer? What are the functionalities? It has number of different functionalities. There is something called IP address, which you already know. So addressing, there is something you might have heard about called routing. So addressing, routing, etc. These are the tasks of the network layer. So the network layer is going to receive the actual data where the header, etc. that was introduced by the sender data link layer is trimmed, and that data is received from the data link layer of the receiver, and it is processed further for doing tasks like routing, etc. So let us try to start with a simple protocol which is called the stop and wait protocol. So in stop and wait, the mechanism is pretty simple. So the sender basically, the sender will send a frame. It will send a frame, right? Then it will stop. It will do nothing. Then it will wait until it receives the acknowledgement frame, from the receiver. Only after it successfully receives the acknowledgement from the receiver, it starts sending the next frame. So what we have is basically unidirectional communication of the frames, okay, from the sender to the receiver. The acknowledgements are also sequential, one after the other. One frame received, acknowledgement sent. One frame received, acknowledgement sent. Like that, there is synchrony that is introduced between the sender and the receiver. The communication that takes place by the data link layer of the sender and the receiver in the stop and wait protocol with the adjacent layers are also pretty much simple. So these are basically depicted in this particular figure, and I think because it is quite evident, I'm not going to go through them any further. But I think you understand the essence that, as this name suggests, that stop and wait, you send the frame, you stop, and you wait until you get the acknowledgement from the receiver. This is the stop and wait protocol. Clear, students? Is it clear? Now let me ask you. Very good, very good. You are smart. Okay, so please tell. Who said yes? Who said yes? Tell your name.
Srijan Das.
Srijan. Srijan, now you tell that what is the problem with this kind of protocol before I try to resolve the problem. You try to guess what is the problem with this kind of mechanism. Clear?
So
Very
there is
simple.
no flow control or error control.
No, 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 no. See, flow control only we are doing. Na? We are doing the flow control only by not sending continuously the frames. We send a frame, we wait until we receive the acknowledgement, right? So this is how we are doing the flow control. But the problem is that this is not going to be too efficient, right? So one frame you send, you wait until you receive the acknowledgement. Again, you send the second frame. So like that, things become very slow. So the channel is not going to be utilized properly if you adopt this kind of mechanism. Clear? Okay. Sijon, is it clear?
Yes, sir.
Okay. Now, let us look at something called the timeline diagram between the sender and the receiver. This sort of diagram you must have, when you studied UML, right? In your second year. Did you study UML in software engineering?
Yes, sir.
So you must have observed similar type of diagrams in sequence diagrams, right? So sequence diagrams look very similar. So you see, these are called timeline diagrams. You see, at the sender, at the receiver, you have this time axis going downwards. These are called timeline diagram. Now let us look at this timeline diagram. So with respect to time, what sort of correspondence goes on between the sender and the receiver in the stop and wait protocol? The sender sends a frame. It is received by the receiver after some time. So this is the time axis, right? Vertically down is the time axis. So you see, that is the reason, you do not write it, you do not draw it, perpendicular to the time axis, right? So there is a certain time lag between when the sender had sent and when it was received. So this frame is sent, it was received after certain duration of time by the receiver. Then the receiver basically sends an acknowledgement back. Again, after certain time, the next frame is sent. The receiver sends an acknowledgement back, and the process continues. This is how the stop and wait protocol looks like from the perspective of the timeline diagram. Okay, clear? Now, some problems can happen. Okay, some problems can happen. A frame may be lost, an acknowledgement may be lost, many things can happen. So for this, you need something called the ARQ mechanisms. The full form is automatic repeat request. So you pay attention to the diagram over here. Once again, the same old diagram, but with certain augmentation. So let us say that you have a set of frames to be sent like this. Okay, and these are the frames that are already sent. This is the next frame to be sent, and after that there are few which are queued. At the receiver end, likewise, you have this kind of scenario. The data frames are sent with certain sequence number as shown in this particular figure, and the acknowledgement frames are also sent with an acknowledgement number as shown in this particular figure. The sender basically keeps a copy of the sent frame, and at the same time it starts a timer. So look at the steps. So the sender, it's going to send a particular frame, and then it is going to start a timer. If the timer expires and it has not, by that time it has not received the acknowledgement from the receiver, then it would indicate that something has gone wrong. Either the frame did not receive, frame did not reach the receiver, or the acknowledgement that was sent by the sender, by the receiver, has not arrived at the sender. Either of these two. So in which case the frame has to be resent. So that is the reason actually it was holding on to the copy of the frame until it gets the acknowledgement. And then, after timeout, the timer is restarted while sending the next frame. So basically it is the same old stop and wait mechanism, with this automatic repeat request augmented to it, so that you can have both flow and error control. Okay, clear? So this is the timeline diagram. Have a look at it, exactly like what I had said before. So you have a frame, you send the frame, you start the timer at the same time. Okay, you get an acknowledgement, you stop the timer, you start the timer, send the frame, get an acknowledgement, you send the you have the next the next frame pointer point to the next frame, and you stop the timer. Now, interesting part over here, the frame is sent. Okay, timer is started, the frame is lost in between, so timer will after some time time out. Clear? So if it times out, the same frame, because it has not received the acknowledgement, because the copy of it was retained by the sender, it is going to be resent. The receiver is going to receive, it is going to send. This thing is very interesting. It is going to send the acknowledgement. Now you see, first we received over here, the receiver had received frame 0. It sent ACK1. What does ACK1 mean? ACK1 means that the receiver is signaling to the sender that I have already received 0 successfully. I am now ready to receive frame 1. Okay, so same thing. So frame 1 is sent. Okay, now the receiver receives the frame, and then it is ready to receive frame 0. So every frame like this will be acknowledged. Okay, the receipt of every frame by the receiver will be acknowledged, and so like this, actually this process will continue. So this was the scenario where we had shown you what happens when the frame 1 is lost. So the timeout happens, the process is repeated. Now it might so happen that the frame was received, but the acknowledgement that was sent was lost. So again the timeout will happen, and the frame 0 will have to be resent. Okay, so this is basically the timeline diagram for the stop and wait ARQ mechanism. Okay, now unless you draw and solve these problems yourselves, it will be difficult for you to really have a complete understanding. So it is very important that so at home you take these as the references and try to work on these yourselves. Okay, so the sequence number basically is a field which signifies the frame number basically. Okay, so the sequence numbers are basically wraparounds. So if you are talking about m bits long field, then the sequence number basically starts from 0 and it goes all the way up to 2 to the power m minus 1, where m is the number of bits, and then it is wraparound, so it is repeated, right? So 0 to 2 to the power m minus 1, again 0 to 2 to the power m minus 1, like that. Acknowledgement number, so if frame 0 has arrived safe and sound, the receiver sends the acknowledgement frame with acknowledgement 1. If frame 1 has arrived safe and sound, the receiver sends an acknowledgement with. So this is the mechanism. Now this was stop and wait. The problem with stop and wait is that it is slow. It is slow. So whether it is ARQ or the regular simple stop and wait, it's slow, right? So now we need to understand that can we do better? Instead of waiting to get an acknowledgement of a single frame, can we send a block of frames one after the other, and then wait for some time, and if we still do not get the acknowledgement of the frames, right, whatever frames we have not got the acknowledgement of, then we we resend those frames. So in this mechanism, we have the opportunity of sending several frames before the receiver basically sends the acknowledgements, before receiving the acknowledgements from the receiver. So until the time that you have got the acknowledgement of all the frames, you have to keep a copy of these frames at the sender source, at the sender side. So obviously, transmission wise, it improves the transmission. However, at the sender side, the trade-off is that you have to buffer those, you have to keep a copy of those frames for longer duration of time, right? So so let us have a look at so how it works, right? So let us first try to understand that there is something called the window, right? So this window is basically an imaginary box that covers the sequence numbers of the data frames that can be in transit. Okay, so in each window position, some of these sequence numbers defines the frames that can be sent, and the others basically define those that can be sent. Okay, so the maximum size of the window is basically 2 to the power m minus 1, where m is the number of bits that are being considered. The send window can slide one or more slots when a valid acknowledgement arrives. So let us try to have a look at how the sender side window is going to look like. So the sender side window is partitioned into 4 parts. So the first part contains the frames that are already acknowledged. Okay, actually this is not part of the window, but basically just to show that what actually happens, right? So these frames basically that are already acknowledged, so these are basically the ones. The second part basically are the frames that are sent but not yet acknowledged. So here in this figure, as you can see, that 0 to 6 are the frames that have been already sent, but the acknowledgement has still not been received. The next part, basically 7 through 14 in this example, shows the frames that can be sent but that are not received from the upper layer yet. And finally, these are the frames that cannot be sent at that point because of the frame size that we have considered, which is 2 to the power m minus 1 window size. So window size is 2 to the power m minus 1, not frame size, window size. So within this window, these are the frames which are already sent but not yet acknowledged, and these are the frames that are not yet sent. Not yet sent means that these have not been received from the upper layer yet. Now, after sliding, so it might so happen that these frames, these frames were already acknowledged. Maybe 3 other frames, 0, 1, and 2. These get acknowledged. So now you see that the window size has now shrunk, right? And because it has shrunk, you can now accommodate more frames. So 1501 can be accommodated. Okay. So now you see that after sliding, basically, you see earlier basically so it was over here. The first outstanding frame was over here. Now this first outstanding frame pointer, now it has come to 3. Okay, so 0, 1, and 2 have already been acknowledged. So from 0, now it has come to this pointer. The first acknowledgement, first outstanding frame pointer has come to 3. Okay, and because the window size is 2 to the power m minus 1, now so 3 more frames can be accommodated in the window. Okay, now receiver window, what happens? The receiver basically can accommodate 1 slot at a time. Okay, the sliding basically will occur 1 slot at a time. So when the window slides, that means that the frame has been received correctly at the receiver end. Okay, in which case the sliding basically occurs 1 slot at a time. So in go back in ARQ, which I was showing you little earlier, the size of the send window must be less than 2 to the power m, and the size of the receiver window is always 1, like is shown over here. Less than 2 to the power m means till up to 2 to the power m minus 1, right? And for the receiver window, it is always 1. So this is basically how the this thing is going to look like, right? So let us say that I said that it has to be less than 2 to the power m, right? So on the left hand side, I show you how 2 to the power less than 2 to the power m works, and on the right hand side, I show you that if we have 2 to the power m or more, then it is not going to work. So 2 to the power m, less than 2 to the power m, right? So we have the sender, we have the receiver, frame 0 sent, then frame 1 sent, frame 2 sent. Okay. Now you see that, look at the situation in the receiver side, right? And look at the situation in the sender side. So in the sender side, you see that 0, 1, and 2 have been sent, but the acknowledgements have not been received yet. Okay. Maybe it was lost, or maybe whatever be the reason, the acknowledgements have not been, or it is there in the network somewhere, whatever be the reason, it has not been received. Okay. Timeout occurs. After some time, the timeout occurs, right? Now you see this outstanding frame 3 can be sent correctly. No. So this is not correct. So 3 is also sent, right? Now frame 0, this is something wrong. So what I told you. So now let me correct it over here. So basically 2 was already received, right? Then 3 was also sent, and no, so 2 was received. Now timeout occurs. Timeout occurs. Now the sender basically knows that basically it has not received the acknowledgement of 0, 1, and 2. Then what it will do? It will resend resend 0. It will resend frame 0. So it resends frame 0, right? Now you see that at the receiver has already received 0. So then it can correctly discard the frame 0, which is sent once again. But you work it out over here. If you had the bigger window size, then what would happen is that once you send this frame 0, this 0 would be confused with the wraparound 0, and it doesn't know, whether to accept it or not. Okay, after the timeout. So this is the problem. Actually, that is why it is illustrating, like, why the window size has to be less than 2 to the power m. So this is a more thorough example showing, like, if the acknowledgement is also lost, what is going to happen. So please look at it yourselves. Very simple, the way I walked you through. Here also similar sort of thing happens. So the last mechanism is called the selective repeat ARQ. Okay, here basically the whole idea is that you do not resend all the frames. You do not reset all the frames as in go back in ARQ. So you resend only selectively the frame that has not been received correctly. Okay, so here basically the the size of the sender and the receiver window must be at most 1/2 of 2 to the power m. Okay, so the size is 1/2 of 2 to the power m, means that size is 2 to the power m minus 1. And we follow exactly the same mechanism that I had shown you, the 4 parts, and what exactly happens in selective repeat request, selective repeat ARQ. So here you see in selective repeat ARQ, this is what happens. Okay, if the window size is 2 to the power m minus 1, then correctly the frame 0, which is resent, will be discarded. Okay, however, if it is more than 2 to the power m minus 1, then the frame 0, if you send once again, it will be accepted. Okay, So selectively it has been, so frame 0 has not been received, you send frame 0. Frame 2 has not been received, you identify that and you resend frame 2. You do not do it for all the frames. So this is basically, so you go through this complete example, okay, where yeah, here for example, frame 1 was lost, okay. You do not again send frame 0, right? So no, or you do not again send here you see frame 1 is lost, right? Frame 2 is sent, frame 3 is sent, and then frame 1 has to be resent, right? Why it has to be resent? Because selective repeat ARQ, it says that, if the receiver has not received a particular frame, then it is going to send this negative acknowledgement NAC and piggyback the frame number that it is expecting. So NAC1 means that I have received all the frames except frame 1 till that point. So this negative acknowledgement, when the sender receives, by the time it has already sent frame 3 also, which is fine, then it is going to only resend frame 1. Little complicated, right? So so not too difficult. So you just work out yourselves, then it will be clearer to you. Okay. So just within a minute we'll complete. So piggybacking, piggybacking is basically used to improve the efficiency of bidirectional protocols. So when a frame is carrying data from A to B, it can also carry control information along with it, right? So this is called piggybacking, right? So this piggybacking mechanism is shown over here, how you can do this piggybacking. So along with the, you see the frame, when this frame is sent, right, you can piggyback this acknowledgement also along with the frame, right? So there are piggybacking based mechanisms, we are not going to cover over here. So it's pretty so there are a lot of things that are there in there, but more or less, so this is how this flow and error control basically can occur. Okay. So we are a couple of minutes over time. I'm very sorry about it, but I hope that all of you followed whatever was there.